Hello. So let's say you're trying to solve a linear problem. Linear problems occur quite often in chemical engineering, and I have an example of one here. So we have a gel, and initially there's no solute concentration. It is of length L, but at time 0 we add a solute to the boundary, and we measure the concentration at the boundary to be Ca0. So if you were to write out the governing equation for this, it probably looks something like this, where you have a time accumulation term, a spatial derivative, and the rate that they're related to, or the diffusion constant. So you might ask, what is a linear problem? And a linear problem is just any problem where things aren't multiplied by itself or its derivative. For example, if we're talking about concentration, we have no Ca times Ca terms or Ca times dCa terms. And this allows us to solve the problem in 3 unique ways that are relatively straightforward. So the first way to solve them is numerically. This is where you code up either an ODE solver or a PDE solver, or you take a built-in one, and I'll go through in a later video of how you do that. And you just program it in something like Python or MATLAB. And this just involves figuring out your boundary conditions and seeing how things change with time. The second way to solve these is via similarity solution. And this method involves the idea of boundary layers. And so you create a variable eta, and this relates how the boundary layer develops. The final way to solve a linear problem is the finite Fourier transform, or FFT. And this involves eigenfunctions and creating basically a basis function, and we create a solution that's an infinite series summed. And I'll go through that a little bit. So before we solve anything here, we have to non-dimensionalize the problem. And there's a few reasons we do this. Mainly, it makes the problem easier. Because if we non-dimensionalize something, it doesn't matter what the diffusion is, or what the time scale is, or what even the concentration is. If things just vary from 0 to 1, they will always just vary 0 to 1, and then you can go back to whatever the solution is from your non-dimensionalization. And the other reason we do that is because it can apply to other problems. And so in this case, we did write it in terms of the concentration, but you could think of an analogous problem where you do temperature or, in some sense, velocity. But this is why we non-dimensionalize things. So the first way is to solve it, like I discussed, numerically. And so here I go through, you can pause the screen and look through kind of the non-dimensionalizations that we go here. So here we have the governing equation, and we want to create a variable, a non-dimensional variable, eta, from 0 to 1. And the reason we choose that is just because it makes more sense to solve things from 0 to 1. There's no particular reason. You could do 0 to 2 or whatever. And so we know at the boundary that the initial or so we create a similarity variable like this, but we know at the boundary, we want it to be 1 because that's the highest concentration that there is. And we know at the end that we want it to be 0 because that's a concentration at this boundary. So if we write the non-dimensional variable, you get something like this. And now we want to get rid of this diffusion term because diffusion can change if we were to move from one problem to the other. So, first we non-dimensionalize x, and then we take out L, and then we can create something like this, and we can wrap it all into the time term, and we develop this tau, which just non-dimensionalizes everything. And so once you get an equation like this, we can just plug it into Python, and I'll go through an example of this in another video, and we could just solve this equation by creating a little bit of a PDE solver. It's still not necessarily the most trivial to solve, but it makes the problem a lot easier than it was before because we don't have to worry about the length or about L or anything like that. So the second method that I discussed was the similarity solution. And this one has a severe limitation in our problem because it requires an infinite domain. Once you have a boundary, stuff can reflect off the boundary, which causes the solution to change in a unique way. So similarity solutions works off the idea that as you go in one direction, another direction scales the same way. So in this case, we have a time variable tau, and we're saying that the square root of tau scales like x. And so we use that fact to create a similarity variable, and we non-dimensionalize just the same as we did before because this is the same. And so you write out a governing equation, you get something like this, and you apply the boundary conditions. So as once before, we want theta to be 1 at the boundary, and we want really far away to be 0. And if you were to solve this equation, you get something written in terms of the error function. And so this is actually a pretty good approximation of our finite solution, so our solution with a boundary of arbitrary length L for early times, right? Because at early times, you can approximate the domain being infinite because it is basically infinite when time is really, really small. So the final method is the finite Fourier transform. And the map for this is quite complicated, and it doesn't actually really matter. You can write things in terms of other functions of a basis function, and then we multiply things together to get the true solution. So because it's a linear problem, the true solution is a sum of a bunch of other arbitrary solutions. So in this case, we create an arbitrary function f, and we have our basis, or we have our FFT solution here. We add them up together. The math for it is quite complicated. You can look through the solution here. It doesn't actually really matter. But in the end, you apply the boundary conditions, you're able to solve for it, you find the basis function out to be this, and then you can solve the differential equation for it. And once you do that, you can solve it in terms of this. And then you can write the total solution in the sum of both our steady state solution, that's the 1 minus x, and our FFT solution. I guess they're both FFT solution, but all the crazy math we did before to get our total solution here. And so in the next video, or in a later video, I'll describe what happens when we change the number of terms we add up and what does this look like as time increases. And so this is actually related to our numerical solution because they should be the same. It doesn't have the same limitation as our similarity solution because there's no difference, or because there's no difference in like the boundary lengths. So for the similarity solution we had an infinite boundary, but in FFT we can use our basis function to create a finite boundary in one direction, and it should equal exactly the numerical solution for large n. Because if we just add a few of these terms, so the first, like, let's say 2 or 3 terms, the sinusoidal part won't add up correctly. So if you're interested in coding this up, please look in the playlist or click the link in the description for the next video. Thank you.